Welcome to this video. Um, in this video, we'll be constructing a galvanic cell between zinc and copper metal, and we'll also be answering the questions that follow: the energy conversion in this cell, the structure of the cell, the chemical reactions that occur in this galvanic cell, and calculating the initial EMF produced by this galvanic cell, and lastly the cell notation. So first of all, this is a galvanic cell. So in a galvanic cell, we're trying to generate electricity from chemicals. So we use chemicals to generate electrical energy or electricity. So that answers our first question of what is the energy conversion in this galvanic cell. So the energy conversion is chemical energy to electrical energy. So that is the energy conversion in a galvanic cell. And how does a typical structure of a galvanic cell between zinc and copper look like? So first of all, we have two containers. We have two separate containers, and these containers are filled with a solution which we call an electrolyte. So now in this example, we are very specific that this is a galvanic cell between zinc and copper. So we're going to insert the zinc electrode in one of the containers and the copper electrode on the other container. So here we have zinc and here we have copper. And we have a voltmeter, which is used to measure the potential difference or the initial EMF which is generated by this galvanic cell. So that is the voltmeter. And the last component which completes the circuit is what we call a salt bridge. Right. So this is a typical diagram of a galvanic cell between copper and zinc. So I'd like to first discuss the electrolytes. So we have two containers filled with an electrolyte, and an electrolyte is a solution which contains ions, positive and negative. So it would be cations and anions, and these ions enables the electrolyte to conduct electricity, right? So now I want us to predict the formula of the electrolyte, or the chemical name of the electrolyte in this cell, and the formula or the chemical name of the electrolyte on this cell, right? So on the left hand side, we have zinc as our electrode, right? So our electrolyte should be zinc sulfate, which is a solution, so it's aqueous, right? So if we're using a metal that can produce a cation of 2+, we use a sulfate, right? So for example, zinc sulfate. And on the right hand side, we have copper. So our electrolyte would be copper sulfate, right? But when don't we use a sulfate? For example, if you have a metal which is like silver, which can be oxidized to lose one electron, right? So there we would use silver nitrate, so instead of silver sulfate. So that is a typical example where we can use a nitrate and not a sulfate. But in this case, we have zinc and we have copper. So our electrolyte on the zinc side will have zinc sulfate, and our electrolyte on the copper side, that would be copper sulfate. So that is the chemical formula, the chemical name of the electrolytes that we would be using. And we have a salt bridge which contains a solution also, which has ions, which is meant to balance the electrical neutrality on the left hand side and the right hand side, right? And I've also discussed some of the functions of the salt bridge, that it separates the two half cells and it also completes the circuit. And the function of the voltmeter is to actually measure the EMF, or the initial EMF, that is produced by this galvanic cell, right? So this is the typical structure of this galvanic cell, right? So we have answered the energy conversion, and we have looked at the typical structure of this galvanic cell. So let's now go to the chemical reactions. So with the reactions, one metal will actually undergo oxidation, which is the loss of electrons, and the other metal will undergo reduction, which is the gain of electrons. So I just want to discuss a guide on how to actually see which one will undergo oxidation and which one will undergo reduction. So we use table 4b. There are two tables, which is 4a and 4b, but then we're going to be using table 4b for our standard reduction potentials. Right. So it has a list of half reactions, and it also shows you the E theta values for each reaction, right? So a guide on how I use this one is that the one that is on top will undergo oxidation, and the one that is on the bottom, that will undergo reduction, right? So for example, in this galvanic cell we have zinc and copper. So if we take a look at the table 4b, zinc is actually on top of copper. So the half reaction is written like this. On table 4b, and that is zinc, and the one for copper is copper 2 plus 2 electrons, then you get copper. So now also the E values, or the E theta values, for zinc is 0.76, and the E theta value for copper is positive 0.34. So this is how these two reactions are arranged in the table 4b. So using this rule is that the one on top will undergo oxidation and the one on the bottom will undergo reduction. So we can see that from table 4b, zinc will be oxidized and copper will be reduced, right? So if zinc will oxidize, so these are the reactions. If zinc will oxidize, the oxidation half reaction is that zinc will lose 2 electrons. This is the oxidation half reaction. And copper would be reduced, so it means copper 2 plus will gain 2 electrons, right? And how does one explain this using this galvanic cell? Is that a part of zinc will lose 2 electrons and it will form an ion Mg2 plus, and these 2 electrons are actually carried to the other half cell. The 2 electrons actually transported to the other cell. So in this electrolyte we have copper 2 plus ions which are ready to gain electrons, right? So when this copper 2 plus sees that there's 2 electrons on this electrode, this reaction would occur and a mass buildup of copper would actually occur on the surface of this electrode, right? So every time this loses mass, it's actually undergoing oxidation, right? 2 electrons to the other side and another copper ion gains electrons, and there is actually a buildup of copper. So as the reaction is occurring, you'd see that the mass of this decreases, the mass of the zinc electrode decreases, and the mass of the copper increases due to a reduction reaction, and the mass of zinc decreases due to oxidation, right? All right, so the electrode where oxidation occurs is the anode. So in this case, the anode would be zinc and the cathode would be copper. And for a galvanic cell, the cathode is positive and the anode is negative, which is something that I'll explain later. But then during the functioning of this cell, zinc will oxidize and copper would be reduced. And since zinc is oxidized, the electrode of zinc will decrease in mass, and since copper is reduced, the mass of the copper electrode would actually increase. So in terms of agents, the metal that undergoes reduction is actually the oxidizing agent. So copper is the oxidizing agent because it undergoes reduction, and the one that undergoes oxidation is the reducing agent. So zinc is our reducing agent in this example. All right, so back to the reactions. We have the oxidation reaction for zinc, and we also have the reduction reaction for copper. And we can also combine these two half reactions in order to get the net reaction occurring. So we actually add all the reactants and all the products, but we have to make sure that the electrons are balanced. In this case, the oxidation half reaction, we have 2 electrons, and the reduction half reaction, we also have 2 electrons. So the electrons are balanced. So we add the 2. We add the 2 reactions plus 2 electrons plus copper, and the electrons actually cancel out. So the net reaction that we obtain is zinc plus copper 2 plus get zinc 2 plus copper. So in this net reaction, we can actually see that copper oxidation number moved from 2 plus to oxidation number of 0. So it means it has gained electrons. And the oxidation number for zinc, it has moved from 0 to 2 plus, so it has lost 2 electrons. So this is the net cell reaction. So that was it with the chemical reactions. And how can we actually calculate the EMF, or the initial EMF produced by this galvanic cell when it's functioning? So we can calculate the EMF, the initial EMF, which is E theta cell. The EMF of the cell is equal to E theta cathode, where reduction occurs, and E theta anode, which is the electrode where oxidation occurs, right? So the E theta cell. So we have decided that according to 4b, or according to table 4b, zinc will undergo oxidation. So this would be at the anode, and copper undergoes reduction. This would be at the cathode. So the E values that we'd be using is this E values given on table 4b. So the E theta cathode would be the one for copper, which is 0.34 volts, minus the zinc E value, which is negative 0.76. Right, so the E theta cell for this cell will be 0.34 minus negative 0.76. So that would be 1.1 volts. So this is the initial EMF produced by this galvanic cell. So let's look at the last part for this video, which is the cell notation. So the cell notation, we start with the anode, and we write the anode ions with their concentration, and we indicate the salt bridge. Then we go to the cathode ions, and then lastly we end with the cathode. So at the anode for this galvanic cell, we have zinc, which is a solid, and the anode ions, zinc will be oxidized to zinc 2 plus, which is aqueous, and the concentration for this is 1 mole per cubic decimeter. And we have the salt bridge. The cathode ions is copper 2 plus, which is aqueous, and the concentration is 1 mole per cubic decimeter. And we have copper, which is a solid. So this is our cell notation for this galvanic cell.